So for the do now, this was similar to the practice that we did on Tuesday of last week, I believe, when we were doing the stuff with Pear Deck. So I tried to pull some similar questions just so we can review the different parts of a voltaic cell. So for number one, it says using the half reactions at the bottom of the voltaic cell, label each of these letters. So for number one, you'll have 1, A, B, C, and D. And you're just labeling as anode, cathode, salt bridge, and voltmeter. And so if we take a look here, again, we'd have like 1A, 1B, 1C, 1D. If you notice down at the bottom, I gave you the half reactions. So remember that in this case, it says it's a voltaic cell. No matter what kind of electrochemical cell it is, whether it's voltaic or electrolytic, it uses redox. So you always have an oxidation half reaction and you always have a reduction half reaction. So if you take a look down at the bottom, we have the two half reactions. We have to figure out which one's oxidation, which one is reduction. So it goes back, reviews oxidation numbers a little bit. So here we have Zn solid going to Zn2 plus 2 electrons. So Zn solid, that is elemental form of zinc, so that has an oxidation number of 0. Zn2 plus, that's plus 2. So then you're thinking, whether you remember oil rig or Leo Gur, you're thinking about electrons. The reactant is losing electrons. The oxidation number is becoming more positive. So Zn to Zn2 plus, this is the oxidation half reaction. Well, remember that the oxidation half reaction occurs at the anode. So C of number one is anode. Oxidation occurs at the anode. They both start with vowels. So then looking at the other half cell, we have copper in a solution of some sort of copper, maybe copper chloride, copper sulfate. But here we have Cu2 plus going down to Cu solid. So now we're going from plus 2 down to 0 in terms of oxidation numbers. You can also look at it with the electrons. Cu2 plus is gaining 2 electrons to become Cu solid. So if we're going from plus 2 to 0, or it's gaining electrons, this is the reduction half reaction. The reduction half reaction occurs at the cathode. Now, once you have the anode and cathode labeled, you can figure out other things about the cell. But then if we look at A and B, we know that we need the salt bridge and the voltmeter. So whatever you have up here, typically you might see it as a V with a circle around it. You might see it as an actual voltmeter, which is a square with numbers on it. But A is the voltmeter. So we have the wire that the electrons flow through because it's a spontaneous reaction in a voltaic cell. The reaction pushes the electrons through the wire. And then B, this is our salt bridge. So the point of the salt bridge, remember, is to keep each of these solutions neutral. Because over time, as oxidation occurs, as the Zn solid actually becomes Zn2 plus, we're going to notice that this is going to start, all of this will become Zn2 plus. So this zinc electrode will actually get smaller in size because the Zn is going into solution as Zn2 plus. The electrons will flow through the wire, and as this becomes more and more Zn2 plus, now we have more positive. Well, in order for the cell to keep working, these solutions need to stay neutral. And so for them to stay neutral, we're going to have some sort of salt in the salt bridge, and cations are going to flow one way, anions are going to flow another way. So that's number one, right? A, B, C, and D of number one. Number two, draw an arrow to indicate the direction in which electrons are flowing through the wire. So I just said you can just draw the arrow, like right on your do now. You don't have to draw the whole cell. But remember that your electrons will flow through the wire. So we have electrons flowing through the wire, but they always flow the same direction. It's not left to right or right to left. It's from one electrode to the other. Electrons flow from the anode into the cathode. So for number 2, you want to just draw the arrow on your paper, you would draw arrow pointing from left to right. Because they go from the anode to the cathode, no matter what, electrons flow from the anode to the cathode because they are lost in oxidation and then they are gained in reduction. And then finally, number 3, which direction will the cations and anions in the salt bridge flow? So let's say that we have, let's do KNO3. So we have K plus and NO3 minus. Your cations always flow one way, your anions always flow another. They're never going to flow in the same direction. Point of a salt bridge is to have each anion and cation going a different way. So remember that cations go toward the cathode, anions go toward the anode. So K plus. And if you want to just write this for number 3, you can write cations flow toward cathode. Okay, so cations to cathode, anions to anode. And the reason your anions flow to the anode, I was just talking about how at the anode, the electrode itself, the piece of metal actually decreases in size because in this case, the Zn is going to Zn2+. So as we get more and more positives in this solution, you're going to have some anions flowing in to keep it neutral. So your anions will flow into the anode. So any questions on the do now? All right, if not, that's it for this. Just trying to review what we did last week, but it seems like a lot longer than last week. So if you don't have them out, get out your electrochemistry notes. So it's Unit 10, Part 2. If you need them, right? If you were taking notes like on a separate piece of paper and you need the notes, I did make some copies over here. So they're right here in the second little, I don't know, folder down. So you can grab some if you need some. I know some people were asking if they could just take notes by hand and then.
Yeah. I can get one.
Are you sure?
You need one?
No, I have one.
Oh, I could grab it for you.
And what we're going to do is we are going to go through, I went through some of the questions from 10.7. So I was looking at calculating cell potential. So we're going to go through, and I'm going to try to answer some of the questions that people had. Now, we're going to do one example today. And we're not doing just one because it's long. We're just doing one example because it just kind of tied only cell potential. As we continue to do more examples, we'll continue to look at cell potential as well. For this week, so I updated lesson plans this morning, so we're going to continue with Unit 10. The last video in Unit 10 will be watched on Friday. That is the last new content video before we start reviewing. So, video 10 of the electrochem unit will be watched Friday. We will do an electrochemistry quiz. It's going to be all multiple choice Friday during the first period of class. It's only going to cover the videos you've watched so far, 10.5, 10.6, and 10.7. We'll do more practice, more examples. We'll have do now questions. But that will be during the first period of class on Friday. Mastering, I was looking at the lesson plans, and our Unit 10 test will be next Thursday because we're done with videos this week. But mastering was supposed to be due, I think, Monday night. So a week from, well, no, I don't even know how many days. 5 days away. It's now going to be Tuesday night. So that's going to give us some more time during class to work and to practice. Remember, it's 20 points, 4 points of extra credit already added in. And then if you want to go back and review anything that we did before break, that 10.5 practice slide deck that we went through with Pear Deck is under the Unit 10 materials in Classroom. So you can go back and you can look through those. I have the questions and the answers all within that slide deck. So if you ever want to go back and review that, I did have some people asking about those slides and where they could find them. If anything changes, I'll always update it in the lesson plans. And remember that all of these slides that I'm clicking through right now, these are all within the Do Now slides. And so you can get those in the Unit 10 materials as well. So some things first with reduction potential. So there were some questions about the difference between reduction potentials and cell potential. So reduction potential, I talked about so in your notes, it's on page 7. So the reduction potential is just that, right? It's the potential for a substance to be reduced. Appendix E. So Appendix E is an entire table that shows the potential of substances to be reduced. They are all reduction potentials. Anytime you're given something on a question, and I'll show you what an AP question would look like, because you're not going to have Appendix E on tests or quizzes, but you're not going to need it because they will give you the reduction potentials. You just have to remember that those are the values. Those are the potentials for something to be reduced. The larger, the positive reduction potential. So if you have a value like fluorine is 2.87 volts, it's a large positive number. That means that fluorine is easily reduced. So the higher the reduction potential, the more likely the substance is to be reduced. If you have a very negative reduction potential, so like on page 7, I kind of gave you a little mini reduction potential chart. You have tin 4 plus at the bottom has a value of 0.15. But if you look at some of the values in Appendix E, like lithium, for example. Now, Appendix E is in alphabetical order. So Appendix E is in alphabetical order, so it's not in numeric order. But if you look at Li plus, for example, Li plus 1 electron yields Li solid, has a reduction potential of negative 3.05 volts. If it's a very negative reduction potential, it doesn't want to be reduced. So instead, we would expect the reverse reaction to occur. So oxidation would occur. That means that Li is more likely to become Li plus. So just remember that they are reduction potentials. The more positive, the more likely it is to be reduced. The more negative, the less likely it is to be reduced, and the more likely it is to be oxidized. So Appendix E, that's lots of standard reduction values, but they are in alphabetical order. On a test or a quiz, on the AP test, you're given the reduction potentials. And again, I'll show you what that looks like in example 1. In a voltaic cell, you always want to identify what is reduced and what is oxidized. What is reduced is whatever has the more positive reduction potential. The one that is oxidized is the one that is the more negative reduction potential. And the reason that I say in a voltaic cell is because voltaic and galvanic cells always have a positive overall cell potential. So if we look at overall cell potential, so this is the difference between the two electrodes. This is the driving force that pushes the electrons through the wire. The value of the cell potential is another way that we can determine if something is thermodynamically favorable. So we have talked about delta G already, right? We're going to relate this back to delta G. If we have a positive cell potential, that's another way that tells us that this overall reaction is thermodynamically favorable or spontaneous. If it's a negative cell potential, it's unfavorable. And on page 7 in your notes, right, I gave you how to calculate the overall cell potential. You take the reduction half reaction, that cell potential, and you add it to the oxidation cell potential. Now, you say, well, but they give us the reduction. Yes, if you flip the reaction, you flip the sign of E. So you always want to make sure that you realize what is oxidized and what is reduced, and you're flipping the signs if needed. Now, there's a change that you need to make to your notes. I was just thinking about everything being positive, apparently. On page 7 of your notes, at the bottom of page 7, it says voltaic galvanic cells always have a positive cell potential. That's true. A voltaic cell is always spontaneous. So it's always going to have a positive cell potential. Here's where you need to change it, though. Right underneath it, it says electrolytic cells. Okay. Cross out where it says positive and write negative, because electrolytic cells always have a negative cell potential. So electrolytic cells always have a negative cell potential. Voltaic cells are always spontaneous. Electrolytic cells are always non-spontaneous. Voltaic cells happen on their own. A battery is a voltaic cell. It powers things on its own. An electrolytic cell needs a power source for it to happen. And we'll look more at electrolysis and electrolytic cells later in the week. So make sure that this gets changed. Again, on page 7, it's bolded and italicized. Voltaic cells are always positive. Electrolytic cells are always negative in terms of cell potential. So what we're going to do, this is the one example that we're going to look at today. And then I want to give you guys some time to work and to practice and review what we've done so far by working on mastering. So if you flip to page 9 in your notes, the top of page 9 says example 1, Al/Zn voltaic cell. This is what an AP question would look like. This is a practice AP question. So notice how they're giving you the reduction potentials already. Mastering, you might need to use Appendix E. If it says use standard reduction potentials, it wants you to use Appendix E. But for tests and for quizzes, you will be given the values that you need. So for part A, it says write the balanced equation for the reaction occurring in the cell, and part B, determine the standard cell potential. So we're given this picture. So this is going to let us review voltaic cells again. So if we take a look at this cell, they give us a key piece of information here that helps us identify everything. Notice that they show us the direction that the electrons are moving. Electrons are moving from Al into Zn. Well, remember that your electrons flow from the anode to the cathode. So that means that Al must be the anode, Zn must be the cathode. And I'm going to label one more thing on here just to help us remember. At the anode, oxidation is occurring. At the cathode, reduction is occurring. Now, here's another way that we could have recognized this if they didn't give us the electrons. And sometimes this is just a small way for us to identify, but notice how NO3 minus is closer to this half cell. NO3 minus is moving down toward the left half cell. K plus is moving down toward the right half cell. While anions move toward the anode, cations move toward the cathode. So there are just some other ways for us to be able to identify where the anode is and where the cathode is. Now, one more thing with this, it tells us that it's a voltaic cell. So it tells us in kind of the name of the example that it's a voltaic cell. A voltaic cell must have a positive cell potential. So when we're figuring out which way the reactions are oriented, we have to make sure that when we calculate the cell potential, that it's a positive number. Otherwise, we've written the reactions wrong and we have to go back and revisit it. So when this says write the balanced equation for the reaction occurring in the cell, first thing that I need to do is I need to make sure I write the reactions correctly because these are reduction. These are both reduction half reactions, Zn2 plus to Zn, Al3 plus to Al. Because you are always given the reduction potential. So you're always given the reduction half reactions. But we know that one of these half cells is oxidation. So I know that the aluminum half cell is oxidation. Which means if this is my half reaction that deals with aluminum, this is showing reduction, Al3 plus going to Al. I want it to show oxidation. So I am going to flip this reaction. So I'm going to just rewrite down here. I'm going to rewrite this flipped reaction. Al yields Al3 plus 3 electrons. This is oxidation. I might just make myself a note here. This is oxidation, so I flip the reaction. The zinc half cell, this is reduction. So the way that this is written is okay. This is showing reduction. Zn2 plus to Zn, it's going from +2 to 0. So I'm just going to write this equation as it's written. So here's my oxidation half reaction. Here's the reduction half reaction. Remember, a voltaic or galvanic cell needs both. You cannot have one without the other. You cannot have 2 reduction half reactions occurring. You can't have 2 oxidation half reactions occurring. So you'll always have to flip one of the reactions because this is always showing reduction. Now, if we think back to balancing redox. I know it's been a while. Remember, you have to balance your atoms. So aluminum, 1 and 1. Aluminum is balanced. Zinc, 1 and 1. That's balanced. There's no O's or H's to worry about. We already see the plus electrons, so we already know how many electrons were needed. But what do I have to make sure to do before I can add the 2 together? Make the electrons equal. So I know I need to make the electrons equal, and then I can cancel them out. Because we never see electrons in an overall reaction. So what can I make both of these electrons equal? 6. So I'm going to multiply this top one by 2. And I'll multiply the reduction half reaction by 3. So if I write this out, I'm going to have 2Al yields 2Al3 plus 6 electrons. And then for the reduction, I'm going to have 3Zn2 plus 6 electrons yields 3Zn. Once our electrons are equal and we've multiplied, then cancel anything that is the exact same on both sides. Remember, they need to be the exact same. Aluminum is not the same as aluminum 3 plus. Because this is Al solid, this is Al aqueous. So what I see is just the electrons will cancel. Once you cancel out anything that can be canceled, then we just add them together. So 2Al solid plus 3Zn2 plus aqueous yields 2Al3 plus aqueous plus 3Zn solid Here's our overall balanced equation. You always have to make sure that your electrons equal and cancel out. We should never see electrons in an overall reaction. So as this cell runs, we have aluminum converting to Al3+, we have Zn2+ converting to Zn. Remember, because this aluminum is becoming Al3+ over time, we would actually expect all of this, and we don't know exactly how much, but we would expect to see the anode decrease in mass because the Al is becoming Al3+, so the solid aluminum is falling into solution. We would expect over time, we would start to actually see an increase in mass on the cathode side because the Zn2+ ions are becoming solid zinc and they're sticking to that electrode. And then part B says determine the standard cell potential. So we're determining the cell potential, E naught of the cell. This naught sign, just like we've done delta G naught and delta H naught, that means standard conditions. So 1 molar solution, 1 ATM. To calculate the standard cell potential, so this is the overall potential, we're going to take the reduction, half reaction potential, plus the oxidation, half reaction potential. Now, if you look in your textbook, you might see it done a little bit differently. It's the same thing. We just flipped the sign already. So reduction. Here was our reduction half reaction. This is a reduction potential. So this we leave alone. Negative 0.76 volts. That is the reduction potential of the reduction half reaction. Now, because we flipped this half reaction, since we flipped the half reaction, we flipped the sign. So plus 1.66 volts. So negative 0.76 volts for reduction half reaction, positive 1.66 volts for the oxidation half reaction because you flip the sign, and then you add them together. You should get 0.90 volts. Now there was a key thing that I talked about in the video, unlike what we did with delta G and delta H when we manipulated the equations. Yes, we multiplied both of these. But even if you multiply, the only thing you do to E naught is change the sign. That's the only thing you can do to E, is change the sign. Because it's a ratio. So since it's a ratio, if you were to increase the number of electrons, you'd actually change E naught, but then it becomes a ratio. So by the time you divide back down, it becomes the same thing. So the only thing you do to reduction potentials is change the sign. Any questions on this example? See, one example, not too bad. So then for the rest of class, so rest of this period into second period, by the rest of this, really, second period. You're gonna have some time to work on mastering. Now, you can choose whether you want to work on mastering or you want to watch tonight's video. Tonight's video is about 8 minutes. I would recommend working on mastering so that you can work with other people. So you can grab a marker, you can work through mastering. And I have up here how the numbers in mastering, the ones you can do, correspond to the videos. So 1 through 5 goes along with videos 10.5 and 10.6. That was from before break. Questions 6 through 12 go along with video 10.7. So that's looking at cell potential. So you'll want Appendix E for that. And then you won't want to do anything after number 12 because the first part is looking along at tonight's video.